This is Mr. Smith here. We are in Algebra 2, Section 6.4, looking at inverse functions. Okay. So the idea of an inverse function is that if I take an original function and it goes from, let's say, 0 to 6, then the inverse function will take 6 and go back to 0. Okay. Or if we're going to go from 1 to 4, then the inverse should go from 4 to 1. Okay. And the idea is if I have an original function, the inverse undoes that. The next major idea about inverses is that there's this symmetry property. Okay? So there's a symmetry about the line y equals x, and so whatever happens on one side, if the original function's up here, the inverse will be reflected down on this side. Okay? And that's going to help us when we look at these functions graphically. If I give you two functions and we look at them graphically, generally we'll be able to have a pretty good idea whether or not they're inverses based on this nice reflection property. Thirdly, if I give you an equation, I ask you to find the inverse. The way that we do this is we switch x and y, and now we resolve for y. Okay, the idea, how do I find the inverse of an equation? We switch x and y, and we resolve for y. Now this problem's a little bit easier because it's linear, but the rules stay exactly the same, even if it is even if it's a nonlinear function, so a more difficult one. Okay, so in this case, everything that y equals 3x minus 5 does, this function y equals x plus 5 divided by 3 undoes it. Okay? Again, how do we accomplish this? We write out the equation y equals something, something, something with x in it, and then I rewrite it, switching x's and y's, and now I resolve. Okay. If I give you two functions and I say, hey, these two functions might be inverses of each other, verify that, or show that. Show that these two functions are inverses, show these two functions aren't inverses. The way we do it is by composing the two functions. So if I have f and g, and these are my two functions, and I think they're inverses, or I want you to verify that they're inverses, I ask you to compose them, f composed with g. But we also have to do it the other way, g composed with f composed with g composed with f, and the result both times has to be that I get out x. Okay, so when I compose the function both ways, the only thing that I'm left with is x. And we have a notation for an inverse function. It is this. F inverse, or f to the negative first power, and this doesn't mean to do any math. It's not saying that we should put 1 over f of x. It's not saying that we should put 1 over f of x. It's just saying that this is the inverse function. It's just a notation thing to indicate that we truly have an inverse. Okay. So here's an example where they give us f of x equals 3x minus 5, and they tell us that this other function, we think it's the inverse, and so they use this notation. I think they use it maybe a little bit prematurely because we haven't verified that they truly are inverses. But to do so, we would compose f of f inverse of x, and we would compose f inverse of f of x. And so when we compose here, we write out function f, and we replace the x with the other function. And here we write out the inverse function 1/3, and we replace the x with the first function, 3x minus 5, and then plus 5/3. Okay, so those are the compositions. And now when I go to simplify this, I should just get out x each time. So here, if I distribute the 3, I'm left with x plus 5 minus 5, which just equals x. Here, when I distribute the 1/3, I'm left with x minus 5/3 plus 5/3, and this just equals x. So I've composed both directions. I've been left with just x. So these two functions are truly inverses of each other. These functions are inverses of each other. Okay. So these are linear functions. This makes our life a little bit easier. we're talking about nonlinear functions, so quadratics or cubics. Okay. So I'd like to focus your attention on this graph here. What we have is y equals x squared. Now I know that there's this symmetry property, so the inverse should be symmetric along this line. The inverse should be symmetric along this line. And so if I flip y equals x squared, I get this graph here. I tried to trace it. My tracing skills are pathetic. So we get that graph there, but there's a problem. It's a little bit of a problem for us. And the problem is that this new graph, x equals y squared, this does not pass the vertical line test that we had for functions. So remember we had this test early on that said if I draw a vertical line through a graph and it hits the graph in two places, the graph is not a function. And we want to focus our discussion on functions and only functions. So we want to emphasize that piece. We only want to talk about these things as functions. And so we have to get a little bit creative. And so here is how we do that. There's a little note down here. If the domain of f of x equals x squared is restricted to only non-negative real numbers, basically positive numbers or 0. If the domain is restricted, then the inverse is a function. Okay, so this is the way we get around this. So imagine if this is my parabola, right? This is my graph y equals x squared. Instead of talking about that whole graph, I'm going to simply restrict the domain over here, and we're only going to talk about half of it. And the reason we do that is because now we'll be able to get an inverse that is a function. Okay. Now here's the good news. The textbook and Smith is going to do that for you. I will already restrict the domain, so you don't have to worry about it, but you need to understand why I'm doing it. And the reason I'm doing it is so that when we take the inverse, so if I take the inverse of this graph, I really get an output, an inverse that is a function. Okay? We want to focus our discussion on functions. And so to accomplish that, I will restrict the domain. Now, if we're talking about a cube function and a cube root function, we don't have to worry about it. Here you can see if I have this blue line, which now is orange, this was the cubing function, or x cubed. And here, let's not do red, let's do green. This is the cube root function. And you can see if I draw a vertical line through this green function, anywhere on this green function, it will only hit once. So the cube and the cube root function aren't any problems there. Okay, we don't have to worry about that piece. Okay. So let me show you this in a problem in just a moment. So we have a test to be able to tell whether or not the inverse of a function is also a function. It's called the horizontal line test. Okay. Again, we want the inverses to be functions, and so we have this really easy test to be able to tell, is the inverse a function? Is the inverse a function? And the idea is if I can draw a horizontal line through the graph and it only hits in one spot everywhere I draw it, then the inverse will be a function. If I can draw a horizontal line and it hits the graph in two places, the inverse is not a function. The inverse is not a function. And so because of this, Smith or the textbook will have to restrict the domain. In this case, we just say x is greater than or equal to 0. And I will be the one who does that. Okay. I will take care of that for you. And you'll just see me make a little comment. The domain will be x greater than or equal to 0. Okay, I will do that, and the reason I'm doing that is so I can make the inverse also be a function. Okay. So here we go. Consider the function y equals 2x cubed plus 1. And they ask the first question, is the inverse a function? Is the inverse a function? So let's first start by taking a look at the graph of y equals 2x cubed plus 1. And if you have your graphing calculators, you can graph this there. I have graphed this already, so I have a rough idea that it looks something maybe like that. Just roughly. It's a rough sketch. So does that pass the horizontal line test? Does that pass the horizontal line test? The answer is yes. I can draw a horizontal line through any point on that graph and I'll be okay. So is the inverse a function? The answer is yes. Yes. Why? Because it passes the horizontal line test. So now how do I find the inverse? That's the next question. How do I find the inverse? So this f of x is really just like a y. So this really says y equals, so y equals 2x cubed plus 1. And now the rule is I switch x and y. So x equals 2y cubed plus 1, and I solve for y. So x minus 1 equals 2y cubed, divide by 2, x minus 1 over 2, take the cube root, and y equals the cube root of x minus 1 over 2. Okay. Number one, we use the horizontal line test to verify that it does have an inverse, and the inverse is a function. Number two, we switch the x and the y, we solve for y, and now I can tell you exactly what that inverse function is. Here it is. Okay, so let us take a look at number 2 here, y equals 2x to the 4th plus 1. Again, we have our graphing calculators, and if we take a look at the graph here, we'll get something that's not truly a parabola. It's a little bit more U-shaped. I apologize, this should really be more squared. So the question is the inverse a function? Is the inverse a function? And by looking at the graph, no. It fails the horizontal line test, so the inverse is not a function. So now Mr. Smith is going to modify the problem. And I'm going to say, here's our function, f of x equals 2x to the 4th plus 1 for x greater than or equal to 0. And now I am restricting the domain. I'm changing the problem. I'm restricting the domain. And what that'll do for us is it'll take off this side of the graph. And now, does this pass the horizontal line test? Yes. Okay, so I'm modifying the problem so that it'll pass the horizontal line test. Now we can talk about the inverse. How do we find the inverse? We come back here. This is the same idea as y equals. So y equals 2x to the 4th plus 1. I now switch x and y. X equals 2y to the 4th plus 1. Subtract the 1. X minus 1 divided by the 2 is y to the 4th. And I 4th root everything, and I get y equals the 4th root of x minus 1 divided by 2. And graphically, if this is the line y equals x, then the inverse piece will be this piece right here, like that, something like that. There. And so the inverse is a function as well. And that was the goal. We want our inverses to be functions. I'm going to skip number 3 and conclude. We'll ignore the marks. Conclude with this problem. Okay. This problem is a little bit more difficult than the questions I'm interested in, but I think it's a good summary of what we need to hit. So, from our limited experience with these types of graphs, does anyone recall what type of graph function this is? All right, looking at this graph, could this be quadratic? right? Quadratics are in the shape of parabolas, so that doesn't make sense. So what type of graph is this? This is a cubic graph. This is a graph of a cubic function. Okay. And with your limited knowledge, you should be able to spot that and see that's a cubic graph. Okay. So if I have x cubed and I want to talk about the inverse, what kind of function is an inverse of x cubed? If I have x cubed and I want to talk about the inverse, what kind of function is an inverse function of x cubed? Just the cube root. Just the cube root. Okay? So I look at choices A and choices E and I say, well, wait, that's not a cube root. Hey, that's not a cube root. Okay? So the question is, how did I originally know the function was a cubic? By looking at the graph. Okay, just by recognizing the graph. We've seen these before a little bit. So hopefully you have enough exposure to that to know that that's a cubic graph. And to know that the inverse, right, because the question asks, what's the inverse? So the inverse has to be a cube root. Now they give us a point 0, negative 2. 0, negative 2. So the original function takes 0 to negative 2. So the inverse function must take negative 2 back to 0. Okay. So the original function takes 0 to negative 2. So the inverse must take negative 2 and go back to 0. That's the meaning of inverse. So when I plug in negative 2 into my remaining choices, negative 2 plus 2 is 0, times 2 is 0, cube root of 0 is 0. So that works. When I plug in negative 2 here, I get negative 4 times 2 is negative 8. Cube root of negative 8 is not 0. So that's out. Lastly, if I plug in negative 2 here, I also get 0 times 1/2 is 0. Cube root of 0 is also 0. So I'm between choices B and D. So lastly, the last thing I'm going to do is I'm going to come up with another point. There are a few other options you have. Maybe you could try to graph these two functions. Maybe you could try to come up with the equation of this line, but I'll tell you what, that's going to be a hard problem to come up with the equation of this line. So instead, let's come out with another point like this one. We'll say this is 2, 2. It's pretty close anyways. If not, we're going to be in trouble. So let's say it's 2, 2. And so now the original function takes 2 to 2, so the inverse function must take 2 back to 2. Okay. So when I plug in 2, here I get 2 plus 2 is 4, times 2 is 8, cube root of 8 is just 2. So that looks pretty good. Here when I take 2, 2 plus 2 is 4, times 1/2 is 2, and the cube root of 2 is not 2. I realize that's a lot of 2's. Good thing this is on a video. You can play it in slow-mo. Let me do it one more time. 2 plus 2 is 4, times 2 is 8. Cube root of 8 is 2, so it works. 2 plus 2 is 4, times 1/2 is 2. But the cube root of 2 does not equal 2. So D is out, and choice B must be the correct answer. Okay. But I like this problem because it helps us build the idea that if I have a cube function, the inverse must be a cube root function. Okay. Also, whatever the original function does, the inverse function must undo it. Those are key ideas. A third idea is there is a symmetry. So if you were to graph maybe choices B and D, we should see a symmetry about this line y equals x. So whatever happens on one side of this line should be mirrored. And I won't try to draw the symmetry because it will look pathetic. But you should see a symmetry about the line y equals x. Okay? And so this concludes section 6.4. Thanks for your attention. Again, how do we find our inverses? We switch x and y and resolve for y. How do we verify inverses? We compose the two functions both ways, and we should get out x, and that's it. And the last idea, sometimes on nonlinear functions, the textbook or the teacher will restrict the domain so that the inverse is a function. Those are the main ideas from this section. Thanks for your attention. See you next time.